Hello. Okay, sorry for being late. I mean, you can work on Kubernetes, on AIML, on whatever thing, and you cannot switch a standard display, so apologies. So let's start, let's get the thing going, and let me try to tell you a tale here, an adventure that I had to go through in Kubernetes. So once upon a time, like all the histories start, in the great kingdom of Kubernetes, a new and terrifying maze appeared. So my name is Antonio, and as I say, I'm going to try to go through this maze during the next minutes, okay? Just to clarify, this is real. This is not something that I'm putting a twist of adventure here, but this you can follow all these things in the GitHub issues, pull requests, and so on. So let me introduce myself. I'm not a knight. I work at Google. I work in SIG Network. And I don't cast spells or do all these magical runes of connectivity. I just try to make Kubernetes networking better for all of you, okay? Better means it scales. The less that you have to know of Kubernetes networking, the better. The more performant that it is without you having to tune anything, the better. So that's our work in SIG Network, okay? So, but it's not that I work alone, right? There are other knights like Sir Tim or Sir Dan Winsip or princess warriors like Surya and Nadia. And we have another friends too, right? We have the people in the networking plumbing group. They develop these multus that most of you know, right? You can attach multiple network interfaces. They also have a lot of other projects that use device plugins to attach RDMA NICs and all these kind of things. Then we have another projects that are implementing Kubernetes networking, right? Most of you use Sirium or Calico these days. They use eBPF magic or NF tables spells to create services, ingresses, network policies, and all these kind of things. And we have another groups within SIG Network that are working in developing new spells, right? The Gateway API people. These people is focused more on the service. So we had Ingress and they evolved the API to handle more complex scenarios. Okay, but we live in this world of I mean, it's not ideal. You all can have 200 horror histories about Kubernetes networking, but so far it was good enough, right? We were improving one thing at a time, but one day, this is a real character, Vanessa. Vanessa works in Livermore Lab. She opened an issue in Kubernetes. She was saying, oh, I ran all these benchmarks, and they are not working well. And because we are a community and somebody was working in MPI operator and, okay, it is, they are saying there's a network problem, let's call Antonio. And I started to work with Vanessa on the problem. The first thing is that I don't know what you're talking to me about. I mean, you are telling me that this is the network, but I don't know what's the network thing that you're telling me. This is completely different than what I'm used to work with. So we started to go into the problem. Okay, so she was running some benchmarks that basically was running an MPI job, and these MPI jobs, for the ones that are not familiar with the parallel programming, used to have a kind of the terminology in parallel computing is SPMD, that is single program multiple, what is the name? I need to annotate it because I forget always. Single program multiple data. And basically what they do is you need to make a computation that requires so many resources that what you do is you create a single program. You split it in multiple processes, and you split the data and execute it in lockstep, right? So the lockstep here is the key. The lock step means that every single process needs to be coordinated with all the others. So the ones that are not familiar, commonly they use these collective primitives for communication. That's the like MPI. I think that is one of the most common implementation, or Nickel in NVIDIA world, and they allow to express how to communicate data between these processes. So when we're looking at this problem, so she opened a very thoroughly written issue, and we were looking at this problem. The first thing is that it is slow, right? But when you are with networking and somebody tells it's slow, okay. I mean, that is not giving me much information. So the first thing that we found is that it was slow at the startup. And when we started to dive into the problem, we started to saw one thing. So this stateful set creates a headless service. And the headless services uses the DNS to provide a DNS name to the pod. So when the daemon set, the stateful set is created and you have a lot of pods, this means that the service, there is a controller manager that it has the endpoint slice controller, is going to go through all the pods, create an endpoint slice, and there is a component in the cluster, commonly the core DNS component, that is going to look at these endpoint slices and is going to create the DNS records, okay? So basically, when you create the job, and because it has to work at lock step, once all the pods are deployed, you need to have the DNS working at that time. So if you don't have core DNS that is heavily optimized, you can have problems at the scale. So that's why we added in SIG scalability a new SLI that measures the time. We call it DNS programmation delay or something like that, that measures the time that since the last pod in the job is running to the time when the DNS provider has generated all the DNS records. And this is very impactful because we are talking here about, I don't know, large-scale training, 5,000 nodes. So you need to generate 5,000 records. You need to pay a lot of money for these machines. So if it takes minutes or something, it's a lot of money that you are losing. So I'm talking here a large scale, okay? And when debugging this problem, what I did is I created a script that emulates the DNS system. And okay, when I had 4,000 records, it worked. And when I have 5,000 records, it didn't work. So it's this kind of thing that when you start to look into this, you say, okay, something that it was going to be 1 minute problem is going to be an infinite problem. Basically, what I found is a Golang DNS bug in the DNS resolver. Why? Because DNS has a fixed limit. So DNS uses UDP by default. So it has a 512 bytes. So I don't know how many records can you fit in, but when you have more records that you can fit into the DNS record, you fall back to TCP. DNS set a flag and say, okay, don't use UDP, I don't have space, I'm going to put all the data in TCP. But it turns out that TCP has another limit. And if you do the math, if you are interested on the technical details, you can reach out later. I have a good document about that. The bottom line is that TCP, you cannot carry more than 4,099 records. So that was the bug. Golang didn't know how to handle the problem, and it failed to return any records. So you never have you were never able to resolve any of the pods. So once we got the DNS problem sorted out, the job was running. He uses no local DNS cache also to improve the speed, and we have core DNS tuned. We ran into another problem. And this another problem was reported by another person that this has an interesting use case. So they have a cluster with 7,000 nodes. And by default, they have, I have the number here, so I want to be correct on this. So he have 30,000 headless services. And he mentioned that every day, the users of the cluster were adding 10,000 headless services. I don't know, they run pipelines or exactly what kind of workload they were using. But what you can imagine is that kubelet and kubeproxy or whatever is running the node are watching these services. That means that you have 7,000 nodes, you have about 40,000 services. Neither kubelet, neither kubeproxy use the headless services for anything, but they are watching all this. So you multiply the pressure on the API server and the components is very big. So what we did is to implement a new functionality on the API server. So basically what we added is a new field selector. So for all of you that are used to program controllers or informers, you know when you set an informer, you can specify some kind of server-side filtering. Label filtering is by default, but field selector filtering needs to be added in the API server specifically. So in this case, we improved Kubernetes with that. So since 1.30, I don't remember when I added this functionality, but in 1.30, I think, more or less, your kubeproxies and your kubelets are not watching all these headless services, so they are more efficient and they consume less CPU and memory. Okay, and well, we thought, okay, we are progressing, but Vanessa, can you try again? Well, no luck. I mean, okay, this is good. We are better than before, but this is not working great. The performance is still bad, okay? And then we keep investigating, right? And what was the problem? One of the problems that when you are with these AI ML workloads is that they use a lot of special hardware, right? They use GPUs or they use TPUs. And these hardware, as I said before, these kind of workloads need to communicate in lockstep. So the network is one of the main bottlenecks. You know, the slower or the faster that it goes to the network is going to have a big impact. So traditionally, when I started to look at the problem is, okay, let me understand how this works. So what I found is that you have a CNI plugin. Okay, let me go back. So I was talking about accelerators. Okay, you have GPUs, TPUs, and the network is important. But then to communicate faster, then you have different technologies to allow to communicate faster, right? So in addition to the common NIC that you have in your VMs, you have now RDMA NICs, or you have InfiniBand, or you have, I don't remember. I think that every cloud provider has some kind of different technologies or vendor. But point is that there is no standardization. So then you need to end with multis for configuring an interface, device plugin food to configure another thing, and then eventually both things come together and your workload can use them and communicate between them. But what's the problem with that? That you were using only qualitative attributes, right? So then you say, oh, I'm a device plugin, so I have 8 of these things, but I have Multus, so I have all these kind of NICs. But you are not able to say, oh, these NICs need to go with this GPU. And it's when you end in what I call the hardware topology lottery, right? So you think in a physical machine, you need to think that they already have, as you have a network between the VMs, they already have their internal networks. I'm oversimplifying, right? The people that is an expert on this, please bear with me. It's just to try to have the conversation going. So the GPU and the NIC follows different paths during the machine, called the PCI bridges and lanes. I don't know exactly the terminology. And what happens if you take the short path, you are faster than if you take the large path. And if you take the large path and you go through a hub, you start to create a congestion on that path and impact the performance of the overall node, okay? So with this in mind, what we ended is with a new API in Kubernetes, okay? Okay. So this new API in Kubernetes was the DRA. I think that you all heard about DRA. It was a big thing during the last years. It went GA in 134. And what DRA provides is the capacity for the device to express qualities, right? It's no longer, I have 4 of these, I have 4 of these with names. They become pets, right? And pets with a name and with different things. But it's just not that, right? You want the pet, but you want also to be able to call the pet that you want, right? I want to call Toby and want to call the other thing. But more than that, it's not that you want a specific pet. You want a couple, or you want a compound device, right? You want the GPU X with the NIC Y. And that's what DRA gives you the chance to express, right? You can say, I want GPU in PCI root 0 with the NIC in the same PCI root. So we have constraints in the resource claim that allows you to do that. And the best part is that you no longer need to add with custom node selectors or labels to try to land the things where you go. It's the scheduler understands all these attributes. And the scheduler is going to do the choice for you. So with this in mind, we have a lot of new opportunities to work, right? And then I'm from the SIG network, I said before. SIG network joined the effort because we wanted to solve the networking problem, right? We have all the multi-network problem and additional problems. And DRA was exactly what we were looking for. And we call this effort Kubernetes network driver. So Kubernetes network driver is the use, is not a thing, it's a way of using DRA and NRI to provide network functionality to the cluster. So, and one example of Kubernetes network driver, because theory is great, documents are really cool, but what you want is things that work in your cluster. And that's why I created DRA-net. This is an open source project that works at Google. We ran this in production. They announced it like last week, I think, with the new A4 machines. I don't know exactly the name of the machine. But the point is that DRA-net is a project that works with the NVIDIA DRA GPU driver and allows you to set up this complex topology scheduling. Okay. And, well, as I said, it's open source, it's GA, and it's ready to use. Let me put an example of how DRA-net and DRA GPU driver is different from the current model of device plugins and CNI plugins and chaining and all the stuff. So imagine that you have these 2 heroes. One are with the DRA magic, and the others are the ones with the device plugin and the CNI chaining. Both the heroes enter in the maze, and when they need to fight the final boss or execute some spell in group, the DRA and the GPU and the DRA-net, despite they are from different vendors, they have a common language. They have a join spell that allows them to be more efficient. The problem with the device plugin and the CNI chaining is that they just eventually get it right, but sometimes they get confused and they attack uncoordinated. The result, and these are real numbers. You can see the numbers in my paper that it got published like 1 month ago. The result is that for all these collective primitives that we were talking, you get a consistent 0 variance on performance. You see the blue line, that's the result of using DRA-net and DRA GPU driver. If you see the orange line, that is the result of using the device plugins and the CNI chaining model. And what that means, well, for all the people that use training on multi-node workloads, this means a lot. A lot of money because these machines are very expensive. So with this, what we can also Okay, let me go back. So we have the performance improvements, but it's just not the performance improvements. It's that we also have a better user experience. As I said, is most of the people that use accelerators, the problem is that you don't have there is no enough stock. So the old model of having custom device plugins and CNI plugins and annotations and CRDs makes the users be tied to a specific infrastructure, and their workloads are not portable. So with DRA, the difference is that you have a common YAML that is only, you can see the example, 4 lines, and that you can use in any different infrastructure, because the complexity is in the driver. But for the user, the application is portable. So just to wrap up on the presentation, as you see, it's not that the new AI/ML workloads are different, it's that they use the network differently, right? Things like DNS, we all know that DNS is complex, but at least for me, that I spend a lot of time in networking, I didn't know that DNS was so critical for these workloads, right? We also didn't know that the headless service has huge impact in the queuelet and queue proxy, and was adding such, and in the API server. So 2 things that we learned during this lesson is that we improve Kubernetes to make it more efficient for this kind of workloads. And the second is the other thing is, we wanted users to be focused on the important thing. We want to have same defaults. We want the default configuration to be simple and the most efficient possible. And now with DRA, we are able to achieve that. But this was just the beginning, right? It's not that this is very focused on training multi-node workloads, but there are more AI/ML workloads that are coming to Kubernetes, and the project is fixing. Other kind of workloads is, okay, once you train your model, then you want to expose your model. And this is when inference comes in, right? We have a new project, is Inference Gateway API extension, so Gateway API inference extension, I always forget the order, that solves this problem. You need to expose your model, you need to, and it's able to pick the right GPU with different scheduling mechanisms, so your backends are used more efficiently, and that results in better cost performance model. And the next thing that I'm personally going to work during the next year is to solve the internode topology problem. Because I try to explain how we solve the intranode topology problem. With DRA, this is solved, but then the problem is that all these workloads are spread across multiple nodes. And then to go between nodes, this has to go through a data center. And this is the key part. We need to be able to offer the same user experience that we give to the users with DRA and intranode topology for internode topology. And that's it. That's my history. This was really a maze for me. It was a great adventure, and I just hope that you enjoy it. Any questions? I don't know if you have mics in the center.
I can speak loudly.
I mean, for.
There you go.
Thank you. On the last slide, you mentioned that placing the workloads across different nodes was a problem. For some of these more powerful machines with 8 GPUs or more on them, is that, first of all, is that what you're talking about, trying to get them onto the same node there?
No, let me try to rephrase the thinking. So if you're familiar with the NVIDIA architecture, they had this rail concept, right? So
right.
If you take the rail, that basically is between 2 points to have the fastest path.
The NVLink?
Well, it can be NVLink, or it can be, I mean, that's the complexity, right?
Okay.
It's between nodes, you are going to have different interface with different technologies that they are going to communicate, right? NVLink is one of them, but you have, at Google, we have Rocky and RDMA, and we have another data center, right?
Okay.
So there are you need to be able to offer the workload the fastest path. That's the
Right,
point.
right.
And that's between nodes. And this is right now deep under the every hardware architecture of the data center. So we need to find a way to export this information so you can say, I want the fastest path.
So in the API Gateway project they have, or the new project from the gateway is LLM gateways. Yeah, LLM gateways. They have the concept of an LLM inference pool. Is that meant to encapsulate putting these on nodes that have that high communication between each other? Or do you know?
That's why the other problem of this maze is that there is a moment that is difficult to compartmentalize problem, right? I was focusing more on the problem of inter-node communications between accelerator, right? The inference is exposing this workload, right, to the user. And I'm not an expert in the area, but basically what I know is that they choose to which backend to route depending on different metrics, because there is not the common metric, right? They depend on the GPU utilization, they want to keep it hot, and all these kind of things. So at one point, everything is going to merge, right? We are now building everything, embedding the problem in Kubernetes and trying to generalize, and not trying to be too fast to not commit errors. But yeah, at one point, all these things are going to merge, and the same thing that you have now a service with a volume or whatever, and you just do a Helm chart, the goal is to have the same experience. But we are not yet, for sure.
Understood. Thank you.
Okay, no more questions? Well, thank you. Thank you for coming.